In our previous video, we walked through the hydraulic calculation process for a fire sprinkler system. As required by NFPA 13, these calculations must be documented in a specific format known as the Detailed Worksheet. In this video, we'll get familiar with this table by filling in the data for the sprinkler system that we explored in the step-by-step calculation video, allowing us to see how each value is entered and how the table helps organize the hydraulic data. In this table, the data for each segment of the piping network is entered between two thick horizontal lines. Each section represents a single pipe run between two nodes, capturing all relevant hydraulic parameters, such as elevation, flow rate, pipe dimensions, fittings, and pressure losses. Each cell in the table must correspond directly to its designated header. For example, in the first column of the table, the first cell records the name of the starting node, while the second cell records the name of the ending node. In our example, the starting node of the first pipe segment is node 101, and the ending node is node 102. We enter these values into their dedicated cells in the worksheet. The second column of the worksheet is dedicated to the elevation of the start and end nodes of each pipe section. Before entering values, we must first select a reference plane for elevation measurement. In our example, we choose the test node elevation as the reference. Since the riser length is 9 feet, and we have assumed that all cross mains, branch lines, and sprinklers are at the same elevation, we can conclude that both the start and end nodes of this segment have an elevation of 9 feet. It is important to note that the selection of the reference plane at the beginning of the calculation is arbitrary. We could choose any plane. However, once selected, the reference plane must remain consistent throughout the entire calculation process. In the third column, we record the K factor of the starting node. This value can either be the K factor of a sprinkler or the equivalent K factor of another part of the system for which we want to determine the flow rate. In our example, since the sprinkler is located at node 101, we enter 5.6 as the sprinkler's K factor. In the fourth column, we record the flow rates. The upper cell is used for the flow rate of the starting node, while the lower cell shows the flow rate passing through the pipe segment. The flow rate of the starting node is calculated by multiplying the coverage area of the sprinkler by the required density. In our example, the coverage area is 130 square feet, and the density is 0.15 gallons per minute per square foot. Multiplying these values gives a flow rate of 19.5 gallons per minute. This calculation should also be documented in the notes cell of the 10th column for clarity. The total flow passing through this segment is equal to the discharge from sprinkler 101. Therefore, we enter 19.5 gallons per minute in the second cell. In the next column, we record the nominal pipe size in the upper cell and the internal diameter in the lower cell. In our example, the pipe size is 1 inch. According to table A1632 of NFPA 13, the internal diameter of a 1-inch Schedule 40 pipe is 1.049 inches. In the next column, we record the equivalent length of the fittings or valves. As explained in the previous video, although this section of the piping network includes 1 elbow and 1 T, NFPA 13 allows us to ignore them. Therefore, we leave these cells blank. The next column contains 3 cells. In the upper cell, we record the length of the pipe. In the middle cell, we enter the total equivalent length of the fittings and valves. Finally, in the lower cell, we write the sum of the two values above. In our project, the pipe length is 13 feet. Since there are no fittings in this section, the middle cell remains 0. Therefore, the sum of the two values is 13 feet, which we record in the lower cell. In the next column, we enter the C factor and the friction loss per foot of pipe. For Schedule 40 black steel pipe in a wet pipe system, the C factor is 120. The friction loss per foot of pipe is calculated using the Hazen-Williams formula, which accounts for the flow rate, C factor, and pipe internal diameter. In our example, this value is 0.124 psi per foot. In the next column, we calculate and record the pressure values. For the first segment of the piping network, the upper cell represents the pressure required to discharge the flow rate, which is determined using the K factor of the sprinkler. In subsequent segments, this cell records the available pressure at the starting node, calculated from the pressure changes in the previous segment. In our project based on the required flow rate and the K factor of sprinkler 101, the pressure needed is 12.1 psi. We should record this calculation in the notes cell. In the middle cell, we calculate and record the pressure loss or gain caused by elevation changes. Since the start and end nodes of this segment are at the same elevation, the pressure change is 0. In the lower cell, we calculate and record the minor and major losses. This value is obtained by multiplying the total length of the pipe, fittings, and valves by the friction loss per foot of pipe. In our example, the result of this calculation is 1.6 psi. Now that we've completed all the cells for the first segment, we move on to the second segment of the detailed worksheet. This segment lies between nodes 102 and 103. The elevation of both nodes remains at 9 feet, and the K factor of the sprinkler is 5.6. To calculate the flow rate of sprinkler 102, we first determine the available pressure at this node. This pressure is obtained by adding the pressure changes from the previous segment, which gives us 13.7 psi. Using this pressure together with the K factor of the sprinkler, the flow rate at node 102 is calculated as 20.7 gallons per minute. We should record this calculation in the notes section. The flow rate passing through this section is the sum of the flow rate from the previous section and the discharge of sprinkler 102, which equals 40.2 gallons per minute. The pipe size is 1 1/4 inches, which gives an internal diameter of 1.38 inches. Similar to the previous section, there are no fittings here, and the pipe length is 13 feet. The C factor is 120. And the friction loss per foot is 0.125 psi. There is no pressure change due to elevation, and the total major and minor losses equal 1.6 psi. Filling the cells for the third section is similar to the second. We complete it using the data and method explained in the step-by-step video. In the fourth section, which lies between nodes 104 and 1, we must account for the equivalent T-fitting located at the intersection of the branch line and the cross main, which is equal to 6 feet. The rest of the cells are filled in the same way as in the previous sections. For the next section, between nodes 1 and 2, there is no sprinkler at the starting node. In other words, the system flow does not change upstream or downstream of this node. Therefore, the K factor cell remains blank. In this section, the pipe size changes to 2 inches. The remaining cells are filled in the same way as in the previous sections. In the next section, between nodes 2 and 3, the flow rate changes at node 2 as part of the system flow discharges through the sprinklers on the second branch line. As explained in the step-by-step video, we can simplify the calculations by applying the concept of an equivalent K factor. Since the first and second branch lines are identical, we use the equivalent K factor of the first branch line to calculate the flow rate of the sprinklers on the second branch line. This equivalent K factor is determined by dividing the flow rate by the square root of the pressure at node 1, which equals 17.5. With this value and the pressure at node 2, the total flow rate of the sprinklers on the second branch line is calculated as 87.5 gallons per minute. In the next section, between nodes 3 and 4, the flow rate of the third branch line is calculated in the same way as in the previous section. In this segment, the pipe length changes, and we must also account for the T-fitting at the intersection of the cross main and the riser. In the last section of our example, between nodes 4 and test, we must account for the elevation change, the pipe size change, and the equivalent length of the valves. Since we selected the test node as the reference point for our elevation measurement, its elevation is set to 0. As the start and end nodes in this section are not at the same elevation, we must calculate the pressure change, which results in 3.9 psi. In this section, the flow rate remains unchanged, but the pipe size increases to 4 inches. The equivalent lengths of the flow switch, alarm check valve, and butterfly valve must be recorded according to Table 282311 and the data sheet. By recording the data in the remaining cells, we complete the detailed worksheet, which is acceptable to the authority having jurisdiction. As you may notice, completing the detailed worksheet often requires tasks such as finding the internal diameter of pipes, determining the equivalent length of fittings or valves, performing friction loss calculations, and calculating pressure changes due to elevation. These steps can be time-consuming and may lead to errors. In the next video, we will introduce a free online tool that helps simplify and streamline this process.